Okay, so this is a video tutorial on numbers and numerals, aka number system. Okay, so we are going to learn a few topics and I would like to list them before we move on. So we are studying numerals, and that is numbers and numerals, and then we will move on to study number systems, and these are some of the subtopics we'll be studying. We have sets of numbers, Venn diagram to illustrate real numbers, number line. We will also look at operations on real numbers, approximation of real numbers. We will also look at standard form, also known as scientific notation. We will also study properties of operation, and lastly we will look at binary operation. Let's go on quickly. So when we are asked what is a number, okay, numbers are ideas that represent quantity and quality. So every number is representing a particular quantity of an item, or it is representing the quality. When you say quantity, you are looking at how often an item occurs. It could be once or 5 times or 6 times or 30 times. That is quantity. And we could also be looking at quality, like we have grade 1, grade 2, and then grade 3 electrical gadgets. Okay, so we can use numbers to represent all of them. So they are the ideas behind those representations of quantity and then quality. They are ideas because they are universal. Then we come to numerals. When we say numerals, what do we mean by numerals? When we say numerals, we are referring to the symbols that represent those numbers. So numerals are symbols that represent numbers, or they are symbols that represent the idea of a quantity and then a quality. Okay, all right, so we'll look at some types of numerals. We have the Roman numerals, then we also have the Arabic numerals. The Roman numerals are endless. Okay, we have other numerals like L, C, and D. They use letters to represent their numbers. And then the Arabic numeral, which is the easiest numeral to be brought into the system, the easiest numeral system, it only has 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can use that to represent any number that is writable. It can be used to represent any number. Okay, so we need to keep in mind that numbers range from negative infinity to positive infinity. Numbers range from negative infinity to positive infinity. So we are moving on to look at sets of numbers. Okay, and then the set of numbers, we have what we call natural numbers. When you say natural numbers, they are the set of all whole numbers excluding 0. So natural numbers actually begin from so natural numbers begin from 1 to positive infinity. So from positive 1, it goes on till we get to positive infinity. Infinity is like an H that is lying down. Then we also have whole numbers. Whole numbers are all natural numbers including 0, or we could say that it is the set of all whole numbers including 0. So the first whole number, or the first positive whole number, you could say 0, but usually 0 is considered as a neutral number. That is, it is neither positive nor negative, and it goes on till positive infinity. So it goes on. Then we have integers. When we say integers, we are referring to all positive and negative whole numbers. All positive and then negative whole numbers. So any whole number that is positive or negative can be referred to as what? An integer. So with this, we are starting from negative infinity to negative 2, negative 1, 0, 1, 2, till we get to positive infinity. This is the set of all our whole numbers. So we could see here that natural numbers are part of whole numbers, just that 0 is not part of natural numbers. And then whole numbers are also part of integers, just that the negative numbers are not part of whole numbers. Then we also have negative integers. So when we say negative integers, we are referring to all negative numbers. So they're actually going to begin from negative infinity all the way down to negative 4, 3, negative 2, negative 1, and then it ends with 0. Or we could even say 0 is not negative, so we'll end it with 1. And then with our positive integers, we could start from 1, 2, 3, 4. It goes on till we get to positive infinity, but we don't really have to put positive in front of positive numbers, so we could just say positive infinity. Now we are moving on to rational numbers. When we say rational numbers, they are any form of number that can be written as a common fraction. That is, they can be written in the form a over b, where a and b are whole numbers and b cannot be equal to 0. Okay, b cannot be equal to 0. A has to be a whole number, b has to be a whole number. So any number you can think about, whether a whole number, whether a fraction or whatever it is, they are all referred to as rational numbers. So when you say rational numbers, we could have proper fractions, improper fractions, mixed numbers, integers, terminating decimals, recurring decimals, so on and so forth. They are all part of rational numbers. So any number that can be written in the form of a fraction is a rational number. 1 over 3 is a rational number. 2 over 1, which is the same as 2, is a rational number. 1 on 6 is also a rational number. 5 whole number 1 over 3 is also a rational number. Yeah. Now when we say irrational numbers, we are referring to numbers that cannot be written in the form of a fraction or cannot even be written as a whole number. And as such, we say that they are usually non-terminating fractions, or they are non-repeating, non-terminating fractions, meaning that they do not repeat. With 1 over 3, the decimal form would have given us 0.3333. This is a rational number because it can be written in the form of a fraction. But if you are to find the square root of 2, square root of 3, square root of 5, or any prime number, or the square root of any odd number, you will not be able to have a rational number or to have a fraction. And as such, we say that they are all non-repeating and then non-terminating fractions. As such, we call them irrational numbers. Okay, keep this in mind. The square root of all prime numbers are not rational. They are all irrational. The square root of all prime numbers are irrational. Now, when you multiply two different square root, okay, or two, if you multiply two irrational numbers, it's likely you are also going to have an irrational number. Okay, there is a mistake where they say the square root of an odd number is an irrational number. No, 9 is an odd number, but the square root of 9 is 3. So this is a rational number. Okay, let's keep that in mind. Now we are moving on to the Venn diagram to illustrate real numbers. That is the Venn diagram to show what real numbers are. So we are going to first draw a root diagram or a chart diagram to depict the kind of numbers of set we've looked at so far. So like we said, real number is actually the universal set for all numbers that are countable or foreseeable in nature. Okay, there are other numbers like imaginary numbers and computer numbers. We are not looking at those ones now. So under real numbers can be put into two different groups. We have what we call rational numbers, which is represented by K, and then irrational numbers, that are represented by H. Then we also have, under rational numbers, we also have what we refer to as integers. Integers is represented by the symbol Z. So the set of Z refers to the set of integers. They are both positive and then negative. And then under integers, we have whole numbers. And then under whole numbers, we have what we call natural numbers. So if we are to draw our set, the set of real numbers contains two main subsets. we have rational numbers, that is Q, irrational numbers, which is H. Under rational numbers, we have integers, which may be positive and then negative. Then for the positive integers, we have whole numbers, and the whole numbers we have natural numbers. So if we are to draw a Venn diagram to illustrate this chart we have here, this universal set will be our real numbers. We are going to have rational numbers here, and then we are going to have irrational numbers here. Then inside rational numbers, we are going to have the set of what? Integers. Then inside the set of integers, we are going to have the set of whole numbers. So all those numbers here that are outside whole numbers, they are all supposed to be negative integers. Then inside whole numbers, we are going to have our natural numbers. Okay, so all the numbers we have in here, it is only 0 that will be here. All numbers from 1 to infinity are all natural numbers, so they will be in here. Okay, so basically that is how we draw a Venn diagram to represent the real number system. So we are to look at the number line. Of the number line, we are looking at how we can represent real numbers on the number line. So usually the number line has a 0 at the middle, and then the negative numbers to the right, and then the positive numbers are to the right, and then the negative numbers are to the left. Let's keep that in mind. So we have 0, positive numbers to the right, negative numbers to the left. So any movement in the left direction is a reduction, and any movement in the right direction is an increase. So we are going to represent all these numbers on the number line. So we have 1, we have to represent half and then negative half on the number line. So we are going to draw a number line. We put 0 here. So on the right, we are going to have positive half followed by 1. You could continue as much as you want. Here we are going to have negative half and then negative 1. It goes on and on. That is what the direction, the arrows at the end tells us. Now let's try with number 2. We have 0. On the right, we have negative 1 on 3. Sorry, it should be positive 1 on 3. On the left, we have negative 1 on 3. That's as far as it goes. You could go on and on. Then with number 3, 0. On the left, negative 2 on 3. On the right, 2 on 3 and 3. Alright. Now when we come to number 4, we realize we have an improper fraction. We could decide to change them to mixed fractions or mixed numbers, or we could still maintain them just as they are, and then we'll see how we'll go by it. So as mixed fractions, we are going to have one whole number 2 over 5 here. So we could represent that here. One whole number 2 over 5, that is the negative on the left, and then one whole number 2 and 5, the positive on the right. So basically that is how it goes. Okay, now we also have to learn how to use these two symbols when we are on a number line. Anytime you see an arrow on a number line, it is giving you a range of numbers. So example, if I should put this here, and then I put say 2, 5 here, and then I give this, what I'm saying is my range of values for x is all the numbers from 2 to 5. Let's note that 2 is not part. Okay, when the circle is not shaded, 2 is not part, but when the circle is shaded, then 2 is part. So if I'm to list the range for x here, the range for x will be such that x equals 2, 3, 4, and then 5. Usually another circle would be here with on top of 5 shaded. If initially 2 is not shaded, then I'll have to get rid of 2 in my subset here. Okay, so let's do it for the questions we have here. So here we are being told that x is a subset of real numbers. The symbol here is subset, but x is supposed to be greater than 2.5. So we are going to draw our number line. We would put 2.5 here. It could be followed by 3, 3.5, 4. So x is supposed to be greater than 2.5. So we are going to put an empty circle here indicating that x is not 2.5, but it refers to all the numbers after 2.5. So this is how we are going to put it. So this tells us that in our subset, all the numbers that are greater than 2.5 are the range for x, but then 2.5 isn't part. In question 2, we have x is such that x is a subset of the real numbers, and x is less than or equal to -2. Let's take note of where the arrow points to. You see this symbol here? The greater than symbol points to the right, so our arrow goes to the right. Here we have less than, it points to the left, so our arrow will point to the left. So we have -2, -3, -4, -5. So it is less than or equal to, because it can be equal to -2, we have to shade -2 here. And we put our arrow on top to tell us that it goes continuously, pardon me. Okay, so that is how we put this statement on the number line. Let's go to statement 3 and let's see how to put that in on the number line. We have x to be a subset of real numbers where x is greater than -2, but then it is less than or equal to 3. So this is what we are going to have. First we put our number line down, and let's see, we are ranging between -2 and 3, so we could put 0 here, 1, 2, 3, -1, -2, -3. So since x is supposed to be greater than -2, this is how we put our circle here, and it's supposed to be less than or equal to -3. So we share this part of the circle. Okay, that is what less than or equal to mean, and then our arrow goes this way. So that is telling us that the range of x is from -2, and then it ends with 3. Okay, so -2 is not part because the circle is not shaded, and it continues to 3. Okay, on these next questions we have number lines, and we are supposed to write the truth set for these number lines. So over here we see that it starts from, our circle is on top of -1, but then it continues, it goes on and on and on and on. So we are going to state that x is such that x is a subset of real numbers. and x is greater than -1, and then we close it because we don't really know where it ends. It goes on and on and on. Moving on to question 5, we are supposed to state this the truth set for the number line. So we see that it starts from -1 and ends at 2. So we are going to state that x is such that x is a subset of real numbers, R for real numbers, where x is supposed to be greater than -1. So x is greater than -1, but yet still it is less than or equal to 2. We are using less than or equal to because this is shaded. So this means less than or equal to, and this is what? Greater than. So x is actually in between. So x is 0, 1, and then 2. That is what the truth set means. Okay, so we are to look at number 6. Okay, as we can see, both are shaded here. So to state the truth set, we will go as x is such that x is a subset of real numbers where x is greater than or equal to 1, and then x is also less than or equal to 3. So that is that. Now when we come here, you realize that we have x is less than or equal to -1, and here x is greater than what? -3. So we have to state that carefully. So x is such that x is a subset of real numbers, where first we have to state this value of x. X is supposed to be less than or equal to -1, and then x is supposed to be greater than 3. Okay, others would like to state it this way. Say 3 is greater than x, and then x is less than or equal to -1. Anyhow you want to state it, that will be correct. Now we are studying fractions. When we say fractions, we are referring to a part of a whole number. We earlier on learned that fractions are usually written in the form a over b. Okay, this is how we usually write fractions. Now I would like us to note that there are 3 types of fractions. We have common fractions, percentage fractions, and then decimal fractions. But our main focus will be on common fractions. Okay, so when we say common fractions, they are usually in the form a over b or c whole number a over b, where b cannot be equal to 0. B cannot be 0. And then we also have percentage fractions, usually come in the form, you see them most 50%, usually on the examination script, 70%, so on and so forth. And then we have decimal fractions that come as 12.5, 10.32, so on and so forth. Like I said, we are moving on to focus on common fractions. Now when we say common fractions, there are 3 types of common fractions, or let's say more. There could even be 6 types of common fractions. We have what we call proper fractions. They are in the form a over b, And we should keep in mind that A is the numerator, B is the denominator. The number on top is called the numerator, and the number below is called the denominator. Like we said, B cannot be equal to 0. That is not possible. B cannot be equal to 0. So with proper fractions, usually the number on top is lesser than the number below. So we have such numbers as 2 over 3, 1 over 2, 7 over 8. All of these are what we refer to as proper fractions. Within proper fractions, they are such that the numerator is larger than the denominator as in value. So we have numbers like 5, we have numbers like 15 over 5, 45 over 6, and then the all popular 22 over 7. Then we also have mixed fractions. Mixed fractions, or what sometimes refers to as mixed numbers, are whole numbers written alongside fractions. So we have examples like 3 whole number 1 over 3, 7 whole number 2 over 5, 8 whole number 2 over 3, so on and so forth. But usually all improper fractions are mixed fractions, and all mixed fractions are improper fractions. We'll look at their relations later on. Now we also have to understand the concept of like fractions. When we say like fractions, they are two different fractions or more that have the same denominator. Two different fractions or more that have the same denominator. So when we take 1 over 5 and then 7 over 5, they are all like fractions. So this set of fractions, they are all like fractions because their denominators are the same. If we are to pick 3 on 10 and then 8 on 10 and then 5 on 10, they are all like fractions. Why are they like fractions? Their denominators are the same. Then we also have the concept of unlike fractions. If like fractions have the same denominators, unlike fractions do not have the same denominators. So when I have 1 over 3 and 8 over 10, they are unlike fractions. When I have 2 on 10 and 3 on 5 and 8 on 12, they are all unlike fractions. But we can see that 8 on 10 and then 2 on 10 are like fractions, but the rest are unlike fractions. Then we also have equal fractions. They are also referred to as equivalent fractions. Now when we say equal fractions, they are fractions that have different numbers, or that appear different but they have the same value. They appear different but their values are the same. For instance, if I should put down 3 over 6, this is the same as 1 on 2, because if we are to break down and then cancel out, 3 into 3 is 1, 3 into 6 is 2. So that also gives us 1 over 2. This same 1 over 2 could also be written as 10 on 20 or 50 on 100. They are all equal or equivalent fractions because their values are the same. Alright, now like I said earlier on, the numbers on top are what we call the numerator, and those below, or the number below, is called the denominator. And then whole numbers are also in this form. Mixed fractions are also in this form. We have the whole number, then numerator over denominator, like we saw in the examples. Okay, let's move on. Now we are looking at the simple form or lowest term, that is cancelling out. So all of these have simpler form, meaning that the values of the numerator and the denominator can be reduced, and we can only do this by dividing both the numerator and the denominator by the same number. You have to use the same number to divide the numerator and the denominator, meaning that that number should be capable of dividing both the numerator and the denominator. When we have 24 over 36, for instance, breaking it down, we are going to break this down first by 2. So this is going to give us 12 over 18. What do I mean by 12 over 18? 2 would go into 12. 2 will go into 24 12 times. 2 will go into 36 18 times. So 2 times 18 is 36. 12 times 2 is 4. Yet still we can divide by 2. 2 into 12 would be 6. 2 into 18 would be 9. And that will give us 9. 6 over 9. We can still cancel out. 3 into 6, that would be 2. 3 into 9 would be 3. So our final value becomes 2 on 3. So this is the lowest term. We cannot cancel anymore. This is the lowest term. Now we are going to do same for number 2. Which number can easily divide 35 and 140 at the same time? I believe that number is 5. So 5 would go into 35 7 times. 5 28 times. Can we still cancel out? Of course. 7 will go into itself once. 7 into 28 would be 4. So the lowest term we have here is 1 on 4. We also have 24 and 45. So what can we use? You can decide to use large numbers that can easily divide both, or you could decide to use lesser numbers. Let's try using 3. 3 will go into 24 8 times. 3 will go into 45 15 times. So giving us 8 on 15. Can we break this down any further? No. Okay, so we are moving on to mixed numbers and improper fractions. I said earlier on that we are going to learn the relation between mixed numbers and improper fractions. So what we are going to do is we are going to convert all these mixed numbers into improper fractions. All these mixed numbers we are going to convert to improper fractions. So how do we do that? First, we should keep in mind that the denominator of a mixed fraction never changes. The denominator of a mixed fraction never changes. So whatever you have in the mixed fraction will still be the denominator. Now, how do we get our numerator? First, we multiply the whole number and the denominator, then we add the numerator. So that is going to give us 7 times 3 plus 2. So 7 times 3, that would give us 21 plus 2 all over 3. And our final answer is going to give us 23 over 7. We will later on learn how to convert from improper fractions to mixed fractions. Let's do same for number 2. First, what do we do? Our denominator never changes, so we are going to have 5. Then we are going to have 6 times 5, that is whole number times denominator plus the numerator. So it is multiplication here, addition here. Whole number times denominator, then we add our numerator. Sorry, that was supposed to be 3. So that will give us 6 times 5, which is 30 plus 3 all over 5. And our final answer would be 33 over 5. Then we do the same for this. Let's try and see if we could do it straight away. 5 times 10 is 50. 50 plus 2, that will give us 52. So 52 over 10. So basically that is how it goes. Now let's see how we can change these back to the mixed fraction. First, you ask yourself the number of times the denominator can cancel out the numerator. If you get a decimal, you ignore the decimal. Now we realize that 7 will go into, I think I made a mistake here. No, it's a good thing I came back to correct it. So we were supposed to have 3 as our denominator. Like I said, the denominator never changes. So we were supposed to have 3 as the denominator, and 3 will go into 23 7 times. 3 times 7 is 21. So it will go inside into 23. 3 into 23 is 7 times. There will be a remainder of 2, because 3 times 7 is 21. When you subtract 21 from 23, we are to be left with 2. 21 from 23, we are to be left with 2, then all over 3, which is the same as what we had earlier on. I think my brain is kind of freezing. It's very, very freezing here. Yeah. So when we come to the next question, we have 33 over 5. How do we convert back to that to what we have initially? First, we are going to divide, because first we multiply. Okay, and then we add it, so next we are to subtract. So first, how many times would 5 go into 33? That would be 6 times. 6 times 5 is 30. Now taking 30 from 33, that would give us 3 over 5, which is exactly the same as what we had initially. Now when we come to our last test, 10 will go into 52 5 times. 10 times 5 is 50. Taking 50 from 52 will be left with 2. Oh, what's going on? What's going on? Okay, so we are supposed to deal with mixed numbers and improper fractions. So what we are going to do is we are going to convert these mixed numbers or mixed fractions into improper fractions, and then we convert them back to mixed numbers or mixed fractions again. So here we have 7 whole number 2 over 3. Now what we have to keep in mind is that the denominator never changes. So we are still going to have 3 here. And then we go back and then multiply the denominator by the numerator. That will be 7 times 3. So 7 times 3. Then we add the result to the numerator. So that would be plus 2. Now we all know 7 times 3 would give us 21. Plus 2 all over 3, and our result will give us 23 over 3. We will come back to solve this. Let's try number 2. What do we do first? Our denominator never changes, so we are going to have 5. 5 6 is supposed to give us 30, but let's write 6 times 5 here, our whole number times our denominator plus our numerator, which is 3. So 6 5 would give us 30 plus 3 all over 5, and that would give us 33 all over 5. Let's try and do this straight away. First we multiply and then we add the result to the numerator. So 5 times 10 would give us 50, and 50 plus 2, that would be 52 over our denominator, which is 5. It is quite fast, isn't it? Alright, so now let's do our best to convert our improper fractions back to mixed fractions. So what do we do first? We have to find out the number of times the denominator will go into the numerator. So 3 would go into 23 7 times. Okay, we are all aware that 3 7 will give us 21. So take 21 out of the numerator and you'll be left with 2. Our denominator never changes. So that will give us every whole number 2 over 3. The same happens to 33 on 5. How many times does 5 go into 33? That will be 6 times. Now 6 times 5 will give us 30. Taking 30 from 33, we'll be left with 3 all on 5. Then let's try our last one. 5 will go into 50 how many times? 10 times. 10 times 5 would give us 50. Taking 50 from 52, that is going to give us 2. all over 5. So that is how we change mixed fractions to improper fractions, and then the vice versa. So we are looking at operations on real numbers. So first we are going to look at how to add and subtract fractions. How to add and subtract fractions. So with this, we are looking at like fractions first. We said earlier on that like fractions have same denominators. So 1 over 8 and 2 over 8 are like fractions. And it is easy to deal with them when they are like fractions. So all we do is we add the numerators, the denominator doesn't change. So 1 plus 2 would give us 3 all over 8. Or if you want to write that in steps, we add the numerators and then the denominator is maintained as 8, just one of them. So that will give us 3 over 8. With number 2, we just add the numerators to give us 3 plus 4 all over 5, and that will give us 7 over 5. With 2 over 7 plus 6 over 7, that will give us 8 over 7. You can always cancel out when you are done. Let's look at the subtraction too. It basically follows the same logic. We subtract the numerators, and then the denominators are the same. That is why they are called like fractions. So we have a denominator of 5, and then we have 4 minus 3. So 4 minus 3, that will give us 1 on 5. When we come to this section, 7 minus 3 is 4. So that will give us 4 on 5. 10 minus 5 would give us 5. So we have 5 on 16. And that's as easy as it goes. That is how we deal with like fractions when we are subtracting and then adding them. Now let's come to unlike fractions. How do we deal with those ones? First, you have to find the LCM. Or as easy as it goes, you multiply the denominators. So first, you multiply the denominators. 2 times 5 would give us 10. Then you do cross multiplication. What we have here, 5 multiplies 1 to give us 5. Then 2 multiplies 2 to give us 4. So this is going to give us 9 over 10. It's quite easy, isn't it? We can do the same for all these 3 numbers. Okay, but since there are 3 numbers, there are 2 ways of solving this, and we are going to try all of them. First, you can find a number they can all divide, and we can all attest that 8 is a number that is divisible by 4 and then 2. So we could put 8 here as the denominator. Now you ask yourself, how many times does 4 divide 8? 4 can divide 8 twice. So you multiply 3 by 2, and that will be 6. Plus, that is what we have there. 8 will go into 8 once. So 7 times 1. That is going to be 7, plus 2 will go into 8 4 times. So 4 times 1 will be equal to 4. When we add the numerators, we are going to have 17 all over 8. This could be written as an improper fraction, which is 2 whole number 1 over 8. Now let's look at the second way of solving this. It is just like we did for the first one. We are going to multiply all the denominators. So 4 times 8, that is going to give us 32. And then 32 times 2 would give us 64. So we are going to have 64 here. So first, to get the value for what we are going to have up here for 3, or for the first numerator, 3 is going to multiply 8, and then the answer will be multiplied by 2. 3 will multiply 8, and then the answer multiplied by 2. So 3 times 8 will give us 24. 24 times 2 would give us 48. Okay, and in the same way, we'll put our plus sign down. Then we move on to the next number. Now 7 is going to multiply 4, then it multiplies 2. It will not multiply its denominator. No number will multiply the denominator. So 7 times 4 is going to give us 28. 28 times 2, that would 56. Now when we pick 1 would multiply 4 and then multiply 2. 1 times 4 is 4. 4 times 2 is 8. So we're going to have plus 8 here. Now we add all the numbers. That will be 48 plus 56 plus 8. That will give us 112 and then 64. Now we could find a number that would divide these two numbers appropriately, and I think that number would be so I think there was a mistake somewhere here. I think 1 is supposed to multiply 4 and then multiply 8. Okay, so 1 is supposed to multiply 4 and then multiply 8. 1 times 4 is 4. 4 times 8 is 32. So we have to have 32 here. Let's rub this quickly and then move on. So when we sum up all these numbers, we have to have 136 over 64. Dividing 2 by 8. 8 will go into 64 8 times. 8 will go into 136 17 times. So we'll end up having 17 over 8. And then cancelling out, we'll have 2 whole number, or changing to mixed fractions, we'll have 2 whole number, 2 over 8. Okay, so to solve question 3, we have first to change them into improper fractions. So 2 times 3 would give us 6. 6 plus 1, that would be 7. So 7 over 2. Remember, the denominator never changes. Plus 3 times 2 would give us 6. 6 plus 2 would give us 8. That would be 8 on 3. What do we do first? We multiply the denominators to give us 6. Then we cross multiply. 7 times 3 is 21. 2 times 8 would give us 16. And that would be equal to 37 over 6. Changing to mixed numbers or mixed fractions, we'll have 6 whole number, 1 over 6. Remember, 6 times 6 will give us 36. So subtracting, we'll have 1 whole number, and then that is that. We would have to do same for question 4. Now first, let's change them to improper fractions. 6 times 1 is 6. Plus 5 would be 11. So 11 over 6 plus 8 times 3 would give us 24. 24 plus 7 is 31 all over 8. Our LCM would be 24, since we know 6 can divide 24 and then 8 can divide 24. Or let's go by our normal method. 6 times 8, and that will give us 48. 11 times 8 is 88 plus 31 times would be 186, and that would 274 all over 48. Let's cancel. So cancelling out by 2. 2 into 48 will be 24. 2 into 274 would be 137. So that would be 127 over 24. In all, we are going to have it in the form of a mixed fraction, and that would be 5 whole number, 17 over 24. Now let's move on to subtraction. It follows the same method. So first we find our LCM. 4 times 3 is 12. Then we cross multiply. 3 times 3 is 9. 4 times 1 is 4. So this will give us 5 and 12. As easy as it goes. Let's look at some more examples. We have mixed fractions and we are supposed to subtract. So first we change them to improper fractions. 3, 2 is 6. 6 plus 1 would be 7. So 7 over 3 minus 4 times 1 is 4 plus 1 would be 5. So that will be 5 on 4. Our LCM would be 12. 7 times 4 is 28. And then 3 times 5 is 15. Remember, you could always have a negative fraction. Okay, so don't be surprised when you have a negative fraction. So 28 minus 15 would give us 13 over 12, which could also be written as 1 whole number 1 12. Same for number 7. This would give us 3 times 5 plus 1, which would be 16. 3 5 is 15 plus 1 is 16 all over 3. Minus 12 times 1 is 12 plus 11 would give us 23 all over 12. Now 3 times 12 would give us 36. 16 times 12, 192. Then 3 times 23 would give us 69. When we do a subtraction, we have 127 all over 36. And since we cannot cancel out, we write it as mixed fraction, and that will give us 3 whole number 19 over 36. Now we are going to look at multiplication of fractions. This is quite easier than what we did earlier on. If you have any problem with the addition and multiplication of fractions, please go back and review them, and then don't forget to comment any problems you have. Now to multiplication of fractions, what we do when we are multiplying fractions is, if we have a fraction, let's say a over b times c over d, numerator multiplies numerator, denominator multiplies denominator. So we are going to have a times c over b times d. So our answer would generally be ac over bd. It's as simple as it goes. So let's try this. So this is going to give us 1 times 4 all over 3 times 5. And that will be equal to 4 over 15. Now changing this to mixed fractions, 3 2 is 6. Changing this to improper fractions, 3 2 is 6. 6 plus 1 would give us 7 over 3 times 2. 1 is 2 plus 1 will be 3, so 3 on 2. So this would give us 7 times 3 over 3 times 2. So this would give us 21 on 6. But we can still cancel out by 3. 3 goes here twice. 3 goes here 7 times. That will give us 7 on 2. But we could have also done the cancellation at this stage, or probably more preferably at this stage. So we could have had 3 cancelling itself 1, 3 cancelling 7 1. So we would have had 7 times 1 all on 1 times 2, which will give us 7 over 2. So 7 over 2 as an improper fraction would give us 3 whole number 1 over 2. That's as simple as it gets. We have similar here. If we look at what we have, we will realize that the fractions can cancel themselves diagonally. So 5 into itself 1, 5 into 15 will be 3. 7 will go into 14 twice. 7 here 3 times. So we basically have 2 times 1 all over 3 times 3. And this is going to give us 2 on 9. We have 3 fractions to multiply, but then we have to change them to mixed numbers first. 7 times 3 would give us 21, plus 1 is 24. So our first fraction is 24 over 7 times 4 times 2 is 8. 8 plus 1 is 9. So 9 on 2 times 9 times 1 is 9. 9 times 5 would give us 45 all over 2. Now let's see if we can cancel out. Maybe we can, maybe we can't. For sure, 2 can cancel out 24 to give us 12. So we have 1 here. 2 again can cancel 12 to give us 6. So we have to have 6 on 7 times 9 times 45. Each one is over 1. So 6 times 9 times 12 would give us, that would be 648. All over 7 times 1 would give us 7. So that will give us 92 whole number, 4 over 7. Okay, so changing them to mixed fractions, we are going to have 3 times 7 is 21. 21 plus 1 will give us 22 over 7 times 2, 4, 8 plus 1 is 9. So 9 over 2 times 9, 1 is 9. 9 plus 5 is 14 over 9. Now 9 can cancel 9. 2 into itself 1. 2 into 14, 7 into itself 1. 7 into 14 will be 2. 2 into itself 1. 2 goes here 11. So we have to have 11 times 1 as we had here times 2 all over 1 times 1 times 1. Our final answer will be what? 22. So keep in mind that we don't write 1 as a denominator. No, we don't do that. Okay, so our final answer will be 22. Now let's try the division. The division is the same as multiplication. So what we usually have to do is we have to invert the fraction on the right hand side. When I say invert, or we have to reciprocate, we are going to have 1 over 2. Change the division to multiplication, and then we are to have 4 over 1. That is the inverse or the reciprocal of 1 over 4 becomes 4 over 1. The numerator becomes the denominator, and the denominator becomes the numerator. So that will give us 1 times 4, which is 4, and then 1 times 2, which is 2. When we cancel out 2 into itself 1, 2 into 4 2 times, so we have 2 over 1, which is equal to what? 2. Like I said earlier on, we do not write 1 as a denominator. No. We have to do same for this, but first we have to change the mixed fraction to improper fractions. So 4 times 3 is 12, plus 1 would give us 13. Our denominator doesn't change, so it is still 4. Divided by 3, 2, 6 plus 1 is 7. So 7 over 3. And that would give us 13 over 4. The division becomes multiplication, and then we have to reciprocate to give us 3 over 7. So 13 times 3 would give us 39. 4 times 7 would give us 28. So that will give us one whole number, 11 over 28. Then going on, example 3, 7 over 12. We only have to change the second fraction to a mixed fraction, so we have to maintain our division, and that will give us 3 whole number 3 over 2, sorry, that will give us 3 over 2. 2 times 1 is 2 plus 1 is 3. So now this will give us 7 over 12 times 2 and 3. Can we cancel out? Of course. 2 into 12 will be 6. 2 into 2 will be 1. So we will end up having 7 times 1, which is 7. 6 times 3, which would give us 18. So our final answer is 7 over 18. Same process for what we have here. So first we have to find our mixed fractions. 7 times 3 is 21. 21 plus 1 would give us 22 on 7 divided by 4 times 7 would give us 28. 28 plus 5 would give us 33 all on 7. Now this is going to give us 22 over 7 times 7 on 33. 7 would cancel 7. 11 into 33 3 times, 11 into 22 2 times, and that will give us 2 over 3. Now let's try V, where we have a whole number being divided by a fraction. This would give us 6. Every whole number has a denominator of 1. Every whole number has a denominator of 1. So 6 over 1. Then we reciprocate this to give us 3 over 1. Okay, so that is going to give us 18 over 1, which is the same as what? 18. It's as simple as it goes. We have a similar one here, so just put the denominator for 4 here, and that would be what? 1, and that will give us 2 on 5 times 1 on 4. Remember, when you change division to subtraction, you have to reciprocate or inverse the fraction on the right hand side. Can we cancel out? Of course. 2 into itself 1, 2 into 4, that will be 2 times. So we are going to have 1 times 1 all over 5 times 2, and that will give us 1 on 10. Okay, so we are moving on to word problems with fractions. Let's look at our first question. A rod is 10 whole number 7 over 8 meters long. 4 over 9 of it is cut off. What is the remaining? So first we have to look at the fraction that was cut off, and then we subtract it from the total length. So we have 10 whole number 7 over 8. In mixed fraction form, that would give us 87 over 8. So length cut off, that will give us 87 over 8, and we were told that of the 87 over 8, 4 out of 9 of it was cut off. Off means multiplication, so we do our multiplication. 4 into 8, 2. 4 into 4 would be 1. 9 will go into itself. 3 will go into 9 3 times, and then 3 will go into 87. 23. I think that will be 29 times. So that will be equal to 29 times 1 would give us 29. 2, 3 would give us 6. So this is the fraction left. We have to subtract from the total. This is the fraction cut off. We have to subtract from the total fraction to get a fraction left. Okay, so what is our LCM going to be? Our LCM is going to be 24. Now 8 would go into 24 3 times. We have to have 87 times 3. So that would give us 216. 261. And then 8 times 29 will give us 116. So that would be equal to 145. That is when you do your subtraction all over 24. Alright, and if we are to change this to mixed numbers or mixed fractions, we are to have 6 whole number 1 over 24. So this is one way of solving it. There is another way of solving it. Okay, let's try that too, but I'll have to clean this before we move on, so you can pause the video and then copy the solutions if you so wish. So this is what we are going to do. First, we are going to find the fraction left. So the fraction cut off was 5 out of 9. Okay, so the statement says the fraction cut off was 4 out of 9. The fraction says 4 out of 9 of it was cut off. So if you have 9 and then you take 4 out, what you'll be left with will be 5 out of 9. So this is the fraction left. So now all we have to do is multiply the total length by the fraction left. Therefore, fraction left, it's supposed to be equal to 1 minus 4 out of 9. And that will give us 5 out of 9. So length left will be equal to 10 whole number 7 over 8 times 5 out of 9. So that is going to give us 87 over 8 times 5 over 9. Now 3 will go into 9 3 times. 3 will go into 87 23 times. So we are left with 23 over 8 times 5 over 3. And let's see what we are going to have. But before we move on, let me correct this mistake. This was supposed to be 29. Okay, I don't know why I keep getting confused here. So 29 times 5 will give us 145. And then 8 times 3, not 2. 8 times 3 will give us 24. And like we solved earlier, this would give us 6 whole number 1 over 24. So that is our final answer. Now let's look at this question 2. 3 measurements end to end are 4 whole number 15 over 32 centimeters, 2 whole number 7 over 8 centimeters, and 1 whole number 9 over 16 centimeters. What is the total? So total means we are to add all of them. So we are going to have 4 whole number 15 over 32 plus 2 whole number 7 over 8 plus 1 whole number 9 over 16. Now the first step is to change all of them to mixed fractions, and that would give us, so 4 times 32 will give us 128. 128 plus 15 will give us 143. So we have 143 over 32 plus 2 times 8 is 16. 16 plus 7 is 23. So that will be 23 all over 8 plus 16 times 1 is 16. 16 plus 9 would give us 25. So this is what we have. Now let's see what we can cancel out and what we cannot. Obviously, since we are adding, we cannot cancel any of them. So we just have to find our LCM and move on. And we can all testify that 32 is the LCM. So we are going to have 32 here. 32 would go into 32 once. So we are going to have 1 times 143, which is 143. 8 will go into 32 how many times? That would be 4 times. 4 times 43 would give us, 4 times 23 would give us 92 plus 16 will go into 32 2 times. So 2 times 25 would be 50. And that would give us 285 all over 16. Sorry. All over, I think I'm getting a little bit ahead of myself. So that will sum up to 285 all over 32. And in sum, we are going to have each whole number 29 over 32. So that's as simple as it goes. Now we are moving on to comparing and ordering of fractions. If we are to order fractions, we have what we call ascending, that is from the least to the highest, and then descending is from the highest to the least. So we are going to arrange this fraction from the least to the highest and then from the highest to the least. And we are going to do that for all the examples listed here. Okay, so we have 1 over 3, 1 over 2, 2 over 5, 1 over 4. The first step you do when you are converting this is to make sure that they all have the same denominators. That is, the denominators have to be the same. And once the denominators are changing, the numerators will also change. So we have 3, 2, 5, and 4. What will be the LCM for these for these 4 different numbers? The easiest way is to multiply them. Okay, so we could have 3 times 2 times 5 times 4. But in this case, since 2 can divide 4, we won't be multiplying by 2. We will only multiply by 4. So our LCM, 3 times 5 is 15. 15 times 4 is 60. Now we are going to divide the LCM by the denominators and multiply the answer by the numerator. So 60 divided by 3 will be 20. 20 times 1 is 20. 2 will go into 60 30 times. 30 times 1 is 30. 5 will go into 60 12 times. 12 times 2 is 24. And then 4 will go into 60 15 times. 15 times 1 is 15. So now that we have these, the highest numerator is the largest fraction. The highest numerator is the largest fraction. We can tell that the highest numerator here is 1 over 2. So that is going to be our highest. That is descending. We are moving from the highest to the lowest. So we'll have 1 over 2 first, followed by 24. 24 represents 2 over 5. Followed by 20, which is represented by 1 over 3. And least is 15, which is represented by 1 over 4. So half is greater than 2 over 5, which is also greater than 1 over 3, which is also greater than 1 over 4. So this is one way of arranging it. If we are supposed to arrange it in ascending order, then we'll go the other way around. This is the least 4 is less than 1 over 3 is less than 2 over 5, which is also less than 1 over 2. Now we have to convert these two, and the routine remains the same. First, we have to find an equivalent denominator for all of them. We have 4, 3, 5, 2. Like we did earlier, we can tell that the LCM will definitely be 60 because we have the same denominators. Okay. Now basically, I think when we divide 60 by 4, we are going to have 20. 20 times 1 is 20. When we divide 30 times 3, sorry, I think this would have given us 15. 60 divided by 4 would have been 15. 60 divided by 3 would have been 20. 20 times 1 is 20. 5 will go into 60 12 times. 12 times 2 is 24. And then 2 will go into 60 30 times. 30 times 1 is 30. So I think this arrangement has already been done from the least to the highest, which is ascending order. So the descending order will be the other way around. Now let's focus on these examples. Okay, so with question 3, we are to compare 4 over 7 and then 5 over 7. Since they all have the same denominators, we are basically just comparing the numerators. So the number with the bigger numerator is the greater one. So we would say that 5 over 7 is greater than 4 over 7. So it's relatively easier to compare like fractions to unlike fractions. Question 4, we have 5 over 8 and the negative 6 over 8. The negative fraction is always lesser than the positive one, just as we have in numbers, in whole numbers. So negative 6 over 8 is less than 5 over 8. It could also be written as negative 5 over 8 is greater than 5 over 8, sorry. 5 over 8 is greater than negative 6 over 8. When they are negative and we are comparing them, the fraction with the least numerator is the biggest fraction. So 5 over 4 is greater than negative 7 over 4. Yeah. And whether there is, with question 6 for instance, we have negative 3 over 7 and then 4 over negative 7. It doesn't matter what the negative is, it makes the whole fraction negative. So with this we would say that negative 3 over 7 is less than negative 4 over 7. It's basically the same thing. Did I say less than? Okay, I think it's supposed to be greater than. Yeah, negative 3 over 7 is greater than negative 4 over 7, because the lesser than the negative number, the more greater the value. Okay, with what we have unlike fractions, and like we do with unlike fractions, first we have to make sure that all the denominators are the same. So 3 and 5 are going to have a denominator of 15. They are all negative, right? So 3 will go into 15 5 times. 5 times 2 would be negative 10. Minus 5 will go into, let's say 5 will go into 15 3 times. 3 times 4 is 12. So we are going to have negative 12. So to sort them out, negative 12 over 15 is lesser than negative 10 over 15. So in all, what we are saying is that to conclude, okay, negative 12 is 4. So negative 4 over 5 is less than negative, I'm running out of space, negative 2 over 3. Yeah. And to solve for the last one, our LCM would be 20. Negative would give us positive. Okay, so these negatives will cancel out, so we'll be left with 7 over 5 and then 7 over 4. So if the numerators are the same, the one with the least denominator is the biggest fraction. So we could say that 7 over 4 is greater than 7 over 5. But let's find that out. 5 will go into 24 times. 4 7 is 28. 4 will go into 20. 5 times 5, 7 is 35. So we could tell that 28 is less than 35, or 35 is greater than 28. So this implies that 7 over 4 is greater than 7 over 5. Yes. So from here onwards, I'm going to maintain the standard. I'm always going to arrange from the least to the highest. Okay, from the least to the highest. So here we have decimals. It is easier to compare decimals when we change them to fractions, and the decimal place will tell us the denominator. So we have 309. Changing 0.309, changing that to fraction would give us 309 all over 1. Then we count the number of decimal places, 1, 2, 3, so that would be over 1000. Then we have 299, okay, also over 3 decimal places, so we have over 1000. Then we have 999, but that has 4 decimal places, so we are going to have 10,000, and then 3 over 10, because 0.3 has only 1 decimal place, and then 31 over 100, which also has 2 decimal places. So let's find the LCM. Finding the LCM, we are going to use the biggest LCM we have, so that would be what, 10,000. So each one into 10,000, this will go into 10,000 10 times, so 10,000. Then we are going to have 3,090, and then the next number would also be 10,000. 1,000 to 10,000 is 10, so we are going to have 2,990. Next, 999 will be the same, so we are still going to have it over 10,000. And then next we are going to have 10 will go into 10,000 1,000 times, so this would be 3,000 all over 10,000. And then the last number we are going to have is 31, which would go into 10,000 100 times, so that would be 31,000. So right here we can tell that with all these numbers, 31,000 is the highest, followed by 3,090. Sorry, I think I made a mistake. It should be 3,100, not 31,000. 3,100. So 3,100 is the greatest, followed by 3,090, followed by 3,000, then 2,990, then 999. So from the highest, we are going to have 31 over 100, which is supposed to be 0.31, and it's greater than 3,090, which is supposed to be 0.309, which is also greater than 3,000, which is supposed to be 0.3, which is also greater than 299, which is 0.299. I would have to clean this here. And then the least will be 0.0999. So that is how we go about that. Now with what we have here, question 10, we would also have to change everything to fraction. So 0.2 would give us 2 over 10, which is the same as 1 over 5. We already have 1 over 4 as a fraction. 30% would give us 30 over 100, which is the same as 3 over 10. And then 10 would be 10 over 1. So let's do the cancellations we can. So that is giving us 1 on 5, 1 on 4, 3 on 10, and then 10 on 1. So our LCM is to be I think 20. 5 into 20 is 4, so 4 times 1 is 4, and then 4 into 20 will be 5. 1 times 5 is 5. 10 into 20 will be 2. 2 times 3 would give us 6. 1 into 10 is 10. 10 times 10 is 100. So we could tell that probably it has been arranged for us already. But since we are arranging from the highest to the least, 10 would be greater than 0.2, which is also 10 would be greater than 30%, which is greater than 1 over 4, which is also greater than 0.2. So that is that. Now we are looking at approximating and rounding of numbers. That is, we are looking at first decimal place. What do we mean by the decimal place? We are looking at the values after the decimal point. That is what we mean by decimal place. With the number here, we have 5.3612. 5.3612. So what are the values of this? The value of this, like we already know, is what? Ones. What we have here is a tenth. So it is written as 1 over 10. It's referred to as a tenth. What we have here is 100. So 1 over 100. So they are usually in cardinals. 100th. What we have here is 1,000. Also can be written in ordinals. And then what we have here is 10,000. Yeah. Okay, so we could also call 3 as 1 decimal place or first decimal place. 6 would be 2 decimal place or the second decimal place. Third or 3 decimal place. And then there is also 2, which is the fourth or 4 decimal place. Okay, so that's about decimal places. Now let's try and then look at this. Now when you are asked to correct a number like we have in this, we are supposed to correct this number here first to 1 decimal place, then to 2 decimal place, then 3 decimal place. First we have to look at what we call the first decimal place. So 4, as we see here, is the first decimal place. Okay, 4 is the first decimal place. So we are running up to 4. So this is going to be 3.4. But then we have to consider the number after the decimal place we are running up to. If the number is 6, 7, 8, 9, then we have to add 1 to it. So this is actually supposed to be 23.5, because the number after 4 in the actual number is 6. We are to add 1 to 4, making 5. I think I left this out. So if the number after the decimal place you are running up to is either 4, 6, 7, 8 or 9, you add 1 to the number. But if it is 0, 1, 2, 3 or 4, you leave it like that. Now let's try this. What is the second decimal place? The second decimal place is 6. the number after it is 2. It is over here, so we do not do anything to it. So we are going to round this up to, or we are going to correct it to 2 decimal places, and that will give us 23.46. Again, 2 is not above 4. Okay, so we don't add anything to it. Now to 3 decimal place, that is going to give us 23.463. Why did the 2 is the 3rd decimal place? Why did it change to 3? Because there was 5 behind it, and like we said, 5, 6, 7, 8, 9, after the decimal place we are correcting to, will increase it. Okay, so since we have 5 here, we have to increase 3 by 1. Okay, let's move on from here. So we are going to round up this number 2 to 1 decimal place, 2 decimal place, 3 decimal place, up to the 5th decimal place. Now what is the first decimal place? The first decimal place is 3. Now our answer should be 987.3. There is no increase in 3 because the number after 3 is 4. There is no need to add value to it. To 2 decimal place, we are going to have 987.35. 4 is increased because the number after 4 is 5, and we need to add 1 to 4. If the number after it is 3, it is 5, 4, 6, 7, 8, 9. So any number greater than 4 will increase the number behind it when it is rounded up to that number. To 3rd decimal place, our 3rd decimal place is 6, so that is going to give us 987.346. Okay, in the same instance, 6 will increase the value of 5 when we round it out to the 3rd decimal place. Now to the 4th decimal place, that is going to be 987.3456. There is no number to increase 6 by. To 7 decimal places, to 5 decimal places, 987.3456 and 0. 0 doesn't really increase anything, but it is telling us that we could have a number there, but that number is 0. Okay, so that is how it goes. Now we will look at rounding up numbers to the nearest 10, 100, 1,000, etc. So we have 9,873,456, and we are to run it out to the nearest 10, 100, so on and then so forth. So to run it out to the nearest 10, we have to know our place value. This is ones, this is tens, hundreds, thousands, 10,000s, 100,000, and then million. So running up to the nearest tens, this means that when you identify the 10th place value, all numbers behind it should be 0. And when those numbers immediately after the 10th place value or after the set place value is above 4, that is, if they are 5, 6, 7, 8, 9, you must increase the place value you are running up for by 1. So since we have 5 and the number after 5 is 6, when we round up the 10th place value, 5 will increase by 1. So we are going to have 9,873,460. So that is how we round it up. Now round it up by 100. What is the 100th place? That is 4. We have 4. With 4 increase, yes, it will increase because we have 5 after it. So that will be 9,873,500, since 4 is increasing. So all numbers after it must be turned to 0. In the same way, we are running upward the 1,000th place value, which is 3. So we are going to have 9,873,000. Okay, initially there was 4, and 4 is below, so we are not going to increase the value of 3. Now to 10,000, our 10,000 is 7. So to run it up, we are going to have 9,870,000. We all know we don't have to increase the value of 7 because the number after 7 is 3. Now we are to run up to 100,000. 100,000. The 100,000 value we have here is 8. The number after 8 is 7, so 8 has to be increased to 9. So this is going to be 9,090,000. 900,000, not 90,000. Okay, then we are supposed to run it up to 1,000,000. And when we look at this, when you run it up to 1,000,000, we have 9 here. We will have to add 1 to it. Adding 1 to it would make it 10 million. So running up to 1,000,000, we are going to have 10 million. Because the 9 would have to increase to 10 when you add 1 to it. So it becomes 10 million. So that is how we run numbers. We round up numbers. Now we are looking at significant figures. Another name for significant figures is important figures. When we say important figures, in any number you can think about, the first non-zero number is the first significant figure. So if I have 0, 2, 4, 5, the first non-zero number from the left is 2. So 2 is the first significant figure. So in this number we have 3 significant figures, that is 4, 5, and then 6. Again, when we have 0.234, the first significant figure is 3. It's 2. So we have 3 significant figures here also. But then when we have 0, let me change it. When we have 1, 3, 4, 0.86, how many significant figures do we have here? We have 6 significant figures. Okay, because 1 is a non-zero number, followed by 3 to become the second significant figure, 4 to become the third significant figure, 0 is the fifth significant figure, 8 is the next, and then 9 is the sixth significant figure. Again, when we have 13.008, we have 5 significant figures here. So like we said, the first non-zero figure is the first significant figure. So 1 is the first significant figure, followed by 3, 0, 0, and then 8. The first significant figure, second significant figure, third, fourth, and then fifth significant figures. So we are going to learn how to round up numbers to the various significant figures. So we have 742,396. We are to round this up to 4, 3, and 2 significant figures. So to 4 significant figures, we are going to count the first 4 numbers, starting with the first non-zero number. So we are going to have 1, 2, 3, 4. Our first significant figure ends at 3. So we are going to have 742,400. This 3 changed to 400 because the number behind it is greater than 4. So we have to increase the value. So this is 4 significant figures. So to the 4th significant figure. Now let's try the 3rd significant figure. Running up to the 3rd significant figure, we have to count 3, which is 1, 2, 3. So that is going to give us 742,000. Okay, we are not increasing 2 because the number after 2 is just 3. Now to 2 significant figures, we'll have to increase this to or reduce it to 740,000. That's because 2 is not greater than 4, so the values, it is not part of the numbers that calls for an increase. That is 5, 6, 7, 8, 9. Now let's look at how we can round up decimals to significant figures. Now, rounding up decimals to significant figures, we have to pay attention to the decimal point and then the details. We said the first significant figure is the first non-zero number. So the first significant figure is 7, second is 4, third is 8, and then 5 is the first is 7, second is 2, third is 8, fourth is 4. So to round it up to 4 significant figures, the value of this number is not going to be changed. To round it up to 3 significant figures, what is the third significant figure? That is 8. So we are going to have 0.0728. To 2 significant figures, our second significant figure is 2, and the value will increase to 3 because the number behind it is greater than 4. So we are going to have 0.073. Okay, so these are our significant figures. Let's try some more examples. So rounding this up to 1 significant figure, our first significant figure is 9. So this is going to give us 0.009. We are not increasing 9 because the number behind it is 4. Now we are to give 15.072 to 3 significant figures. So 3 significant figures would be 1, 2, 3. So that is going to give us 15.1. Okay, because the number after the third significant figure is 7. Moving on, we have 0.4563 to 2 significant figures. So rounding this up, we are going to have our first 2 significant figures to be 4 and then 5. So this will give us 0.46. We have to increase 5 to 6 because of the value of 6 here. It is greater than 4, so we must add 1 to 5. Right, so question 8 is quite the type I like a lot. We are just running one number up and decreasing the significant figures. So to 4 significant figures, our first significant figure is 2, 8 second, 7 third, 5 is fourth. So this is where we ended. So we are to have 287,500. The third significant figure is 7, and we'll have to increase that by 1 because the number after it is greater than 4. So that would be 288,000. To 2 significant figures, our second significant figure is 8. It's 8 here, so running it up is going to be 290,000. Because of the 7 here, we have to increase 8. Now to 1 significant figure, we'll have to increase 2 to 3. So that will give us 300,000. Now last example on significant figures, we are to round this up to 2 significant figures each. Our first significant figure is 4 followed by 6. So 6 will have to increase to 10, and then 9 would have to increase to 10 because of 6, and then we'll have to add 1 to 4, making it 5. So this is going to be 0.050. So this is 2 significant figures. 5 and 0 are significant figures. So 5 is the first non-zero, and then it affects the 0 after it to also make that 0 a significant figure. With B, our first significant figure is 9, second is 9, and when we round them up, 6 is going to affect 9, making it 10. 10 will also affect 9, making it 10. So this is going to be 0.100. So this is our second significant figure was supposed to end, but it looks like 3 significant figure, but we just obeyed our rule. It just happened to look like 3 significant figures. Okay, so this happens some of the time. Now we are looking at changing common fractions to decimals, and we'll have to use what we sometimes term as the long division. So how do we do this? First, 3 over 4 is the same as 3 divided by 4. So you have to do that division. You could use what is known as the long division method. 4 is dividing 3. So 4 will go into 3 0 times. You introduce a decimal point, then you can add 0 to your 3. So now 4 would go into 3. How many times? That would be 7 times. 7 4 is 28. So when we do our subtraction, we are going to have 2 here. Since 4 cannot go into 2, we'll have to introduce another 0. 4 will go into 2 5 times. 5 times 4 would be 20. Then we can do our subtraction. There is no need for us to add any decimal here again. After the first decimal, there is no need. So that is going to give us 0.75. Let's try it for 2 over 9. That will give us 2 divided by 9. You could do the same for that. So that is 9 is dividing 2. Now 9 cannot divide 2, so 9 into 2 will be 0. We'll have to introduce our decimal point. Then we can add 0 to 2. 9 will go into 20 twice. 2 times 9 would give us 18. And we subtract, we are going to have 2. We'll have to introduce another 0. Now 9 will go into 22 times. 2 times 9 would give us 18. When we subtract, we are going to have 2 again. So we can see that this will be recurring, or it will be repeated. So we write this as this is equal to 0.22. Then we put our decimals or our point on top to show that it is recurring or it is a non-terminating fraction. I believe the same is going to happen for question 3. So this would be 1 divided by 3. So we could rewrite that here. 3 is dividing 1. 3 into 1 would be 0. We introduce our decimal point and then bring it here. 3 times 3 is 9. 3 into 9 into 10 will be 3. When we do our subtraction, we are left with 1. We introduce our 0. 3 into 10 will be 3 times. 3 times 3 is 9. We introduce our subtraction, that will also be 1. Another 0. 3 into 10 will be 3 times 3, 3, 9. We do a subtraction 1, and it will go on like that. So this is equal to 0.333. Since it is recurring, we put this up here. But keep in mind that not all numbers would give us recurrent fractions. Okay, so we have to work them out and be sure first. Now 1 is being divided by 11. Let's try out this one too. So 11 is dividing 1. So 11 dividing 1 would be 0. So that would be 11 dividing 1. So 11 divides 1, 0. We use our decimal point 1, 0 here. Now since 11 cannot still divide 10, we'll have to introduce one more 0 here. Then we can do introduce our 0 here, then we do our division. Now 11 will go into 109 times. 9 times 11 is 99. Doing our subtraction, we are going to have 1. 9. Okay, so now we have 1 here. 11 going to 1 will still not be possible, so we'll have to introduce a 0. Still not possible, then we have to introduce another 0 again. Because we're introducing a second 0, we must bring in one more 0 here. Then we ask ourselves, how many times will 11 go into 100? That will still be 9 times. 9 times 11 is 99. When we do a subtraction, we are going to have 1. And we realize we have to introduce 2 zeros again. So introducing 2 zeros here means we'll have to add one more 0 up here. So it is just going to be repeating in that order. So this is 0.0909 in that order. So we could just make it like that. Now let's try it for 4 over 7. So 4 divided by 7. So 7 is dividing 4. 4 into 7, that is relatively impossible. So we introduce 0. Then we introduce 0 and then our decimal point. That is 4 will go into 7 into 4 would be 0. Introduce our decimal point and then add 0 to 4. So now 7 can go into 4 5 times. 5 7 is 35. When we do a subtraction, we have 5. 7 can't go into 5, so we introduce a 0. Now we are going to introduce 0 to 5. Now 7 into 5 would be what? 7 times. 7 times 7 is 49. So that is going to give us 49. We do our subtraction and then there is only 1. We introduce one more 0. 7 into 10 would be 1. 1 times 7 is 7. We do our subtraction and then there's 3. We could go on and on and on and solve this. Let's just put it into the calculator and see what we are going to. So that is going to give us 0.571428. It will continue at 571428 and so on. So we could just write that as 0.571428. So since it is recurring and non-terminating fraction, we will just state it like that so that we know that this is the value that keeps recurring. Alright, so now we are going to look at how to change decimal fractions to common fractions. Okay, and when you have them like this, they are quite easy. So we are going to write the first significant number as the numerator, then all over 1, then we introduce zeros. Then the zeros correspond with the number of decimal places. How many decimal places do we have here? 1. So that will be 7 over 10. With 0.77, we have 2 decimal places. First significant number is 7 over 1 with 2 significant places, so that would be over 100. And we have 31, 2 significant places, so also over 100. 2 decimal places. Then with number 4, we have 73 to be significant figures. And then how many decimal places? 3 decimal places, so that would be over 1000. Our significant figures are 37 all over 10. Okay, because we have only 1 decimal place, so all over 10. Now for what we have for question 6, we have a non-terminating recurring decimal. How do we change such a figure to a decimal number, or to a fraction, such a decimal number to a fraction? That is quite easy, and we are going to learn that just now. First, we are going to equate our decimal to r. So let r be equal to 1.6 66666. Then we could say that 10r would be equal to 16.666. So what we are going to do is we are going to take 10r, then we subtract r from 10r, and we are going to do the same for the left hand side. So that would be 1.666. Sorry, 10r is, we'll have to increase this to 6 as it continues. So 10r is going to be 16.666666 minus r is 1.666. it goes on like that to 3 values. So this is going to give us 9r equals, and that is going to give us 15. Now we divide both sides by r, then r is going to give us 15/9. So this was the fraction that gave us 1.666666. You can test that out in your calculator. So to deal with this, let r equal 0.1111. Then 10r will be equal to 1.1111, since it is non-terminating and then recurring. So we are going to have 10r minus r equals 1.1111 minus 1 minus 0.1111. So we are going to have 9r here equals, after the subtraction we'll be left with 1. Now we divide both sides by 9, and r will be equal to 1/9. So 9/1 gave us the 0.11111. Let's try same for this. So let r equal 3.222222. Then 10r will be equal to 32.222222. So 10r minus r implies 32.222222 minus 3.222222. Now this is going to give us 9r equals 29. Dividing both sides by 9 implies r will be equal to 29/9. Okay. Now these are some more complex examples. Okay. When we look at what we have here, we have 4 decimal places, 3 decimal places, or 3 significant figures that keep recurring. So we have to keep that. In this type of questions, you don't just multiply by 10, you have to multiply by 1000, because we would like to move all these 3 digits, that is 4, 3, 1, to the non-decimal side. So in this case, let r equal 0.431431. Then we are going to pick 1000r, because it is 3 decimal places that keep recurring. So 1000r will be equal to 431.431431. So now 1000r minus r will be equal to 431 minus 0.431431. Now when we do our subtraction, we are going to have 999r equals 431. No decimal. Stop messing up. 431. So dividing both sides by 999, r would give us 431 all over 99. So in conclusion, r, which was supposed to be equal to 0.431431 equals 431 all over 99. That is 431 over 999. Now let's try the same for this. You can pause the video, have a go at it, and then come back to check if it's correct. So let r equal 0.166666. So we started, let r be equal to 0.1666, and then 10r will be equal to 1.666666, and then 100r will give us 16.666666. So if you notice, the aim is to make sure that after the decimal point we have the same value, so that when we subtract we'll be left with only whole numbers. So this is going to give us 100r minus 10r, and that will give us 16.666666 minus 1.666666. So we are going to have 90r equals 15, because 0.666 is cancelling. All of this will cancel each other out, and then we'll be left with 16 minus 1, and that will give us 15. Now we'll divide both sides by 90. 90 cancels 90, and r will be equal to 15 into itself 1, 15 into 90 is 6, so that will give us 1 over 6, which is equal to 0.166666. So that is how we go by solving such a question. Okay, so we'll move to our next subtopic, and that would be standard form. So writing numbers in standard form is quite simple. All you have to do is place a decimal in front of the first significant number. You multiply it by 10, then you raise to the power of decimal places you have introduced. Let's work it out and see. Our first decimal place is 2. So we are going to put a decimal after 2, and then we will have 3 zeros. Now we have introduced 3 decimal places, so it will be times 10 raised to the power 3. As simple as that. This is 10. Our first significant figure is 1. So this would be 1.0 times 10. How many decimal places have we created? 1. So raised to the power 1. 4,687.02. Our first significant figure is 4. So we introduce our decimal point, and that will give us 68702. The initial decimal point has been moved. Now how many decimal places did we create? We created 3 more decimal places. There was already 2, and we have created 3. So it will be times 10 raised to the power 3. Again, we have 356.07. There are already 2 decimal places, but our first significant figure is 3, so we introduce our decimal point. Then we have 5607. We have added 2 decimal places, so that will be times 10 raised to the power 2. Now we have 41,460. Our first significant figure is 4, so we are going to have 4.1460 times 10. How many decimal places did we create? 4. So raised to the power of 4. That's as simple as it goes. And with what we have here, 3, we are to have from 3,201.7, we'll have 3.2017 times 10 raised to the power 3, because we added 3 more decimal places. Okay, now what if the number is less than 1? Okay, if the number is less than 1, then our power will be negative. So if we have numbers like this, 0.00, so 0.0018, 0.001, our power would be negative. Okay, so what is our first significant number here? It is 1. So we are to have 1.8. How many decimal places did we remove? We have removed 1, 2. We have removed 1, 2, 3 decimal places, so that will be times 10 raised to the power negative 3, meaning that we have removed 3 decimal places. Our first significant number is 1, so 1.0 times 10 raised to the power 1, 2, 3. So we've removed 3 decimal places, and that will be indicated by negative 3. This will give us 2.0 times 10 raised to the power negative 1, because we removed only 1 decimal place. And with this, our first significant number is 4, so we have 4.3216. How many decimal places have we moved? 1, 2, 3. So times 10 raised to the power 3, or negative 3. I usually tell my students to count the number of zeros. So how many zeros do you have? 1, 2, 3. So all these 3 zeros have been removed, so raised to the power negative 3. With this, how many zeros have to be removed? Just 2. So we'll have 5.003 times 10 raised to the power negative 2, because we removed 2 zeros, or we moved the decimal point 2 times. Okay, so always keep in mind that the decimal point comes after the first significant figure. How do we write this? Our first significant figure is 3, so writing in standard form, we have 3.627 times 10. How many decimal places are we taking off? 1, 2, 3, 4, 5. We have 5 zeros too, so we raise the power negative 5. So that is that. Now try pausing this video, come back and check if your answers are correct. Work them out and then come back later to see if your answer is correct. Okay, so this is how it goes. Hope you had them correct. Now we will move on to addition and subtraction of standard form. We can really do addition and subtraction in standard form. Okay, now we are looking at addition and subtraction of standard form. Now there are 2 ways the questions could be set. When the powers of 10 are the same, it is relatively easier to work it out, but when they are not the same, it relatively becomes difficult. So let's look at the first type, where the powers are the same. So since they are multiplying, we could just factor 10 raised to the power 4 out. So we'll have 2.8 plus 1.6, then we factor times 10 raised to the power 4 out, just like factorization. So when we sum this up, this is going to give us 4.4 times 10 raised to the power 4. It is that easy. We can do the same thing for the subtraction. So we will have 2.5 minus 1.6, then we factor 10 raised to the power negative 4 out. So this is going to give us 0.9 times 10 raised to the power 4. When you are subtracting raised to the power negative 4, when you are subtracting decimals, you could just assume that they are whole numbers. So this would appear like 25 minus 16, and that will give us 9. So we write 0.9. It's that simple. But then when you have the powers to be different, the powers of 10 to be different, like we have here and here, also in the subsequent question, what you have to do first is you have to convert them to their actual numbers. When you are done, then you convert it back to index form. So that is what we are going to do now. So 2.8 times 10 raised to the power 4 is going to give us 2, that is 28,000. 4 decimal places, 1, 2, 3, 4. So that is 28,000 plus 1.6 times 10 raised to the power 4 is going to give us 1,600. So when we add this, we are going to have 44,000 I think I messed it up. That is supposed to be 29,600, and in index form, first significant figure, how many decimal points have we introduced? 1, 2, 3, 4. So times 10 raised to the power 4. Let's try that for the subtraction. So this is going to, we are supposed to introduce 4 zeros here. Okay, since we have a power of negative 4, so 1, 2, 3, 4, 2, 5 minus, how many zeros do we introduce here? 5. 1, 2, 3, 4, 5, 1.6. So this is what we are going to have. And then what we do is we can decide to arrange them vertically so that we do our subtraction. So I'll bring this here, give 0.00016. So let me introduce an extra 0 here to make this subtraction more friendly. So 0 minus 6, I have to borrow 10 to this. I borrow 1 from 6 to this side. That would be what? 10. Okay, changing 10s to 1s will give us 10. So we are going to have 10 minus 6, and that will be 4. 5 minus, we will be left with 4 here since we borrowed to the other side. 4 minus 1 will be 3. 2 minus 0 is 0. 0, 0, 0.0. So this is going to be our number. Now writing this in standard form would be equal to 3.4, our first significant number, times 10 raised to the power, how many zeros? 1, 2, 3, 4, 5. I think I made a mistake here. There was supposed to be a 2 here. Okay, and then a 3 here. So this was supposed to be 2.34 raised to the power 4, since we are clearing 1, 2, 3, 4 zeros. So that is supposed to be our answer, and then the 4 is supposed to be negative. Never forget to put that there. So basically that is how we go about addition and subtraction of standard form. Now let's look at multiplication and division in standard form. Okay, as we can see from the question, they are all multiplying. So all we do is we group like tens, and then we follow the laws of indices. So we would have 9.3 times 2 times 10 raised to the power 5 times 10 raised to the power 3. 9.6 times 2 would give us 9.3 times 2 would give us 18.6 times 10 we have to add the powers. That will give us times 10 raised to the power 6. Sorry, that's supposed to be 8. And then this is not in standard form, so we'll have to change it to standard form. We only need one significant, the decimal to be after our first significant number, so that will give us 18.6 times, then we'll have to increase 10 raised to the power 8 to 10 raised to the power 9. So this is how we'll go by it. Now let's try the division. So we'll collect like terms and then divide them. So we are going to have 2.16 divided by 2.7 times 10 raised to the power 6 also divided by 10 squared. So that will give us 0.8 times 10. Since we are dividing the 10, we subtract the powers. So that is going to give us 10 raised to the power 6 minus 2. That will give us 4. So that is our answer. Another multiplication question. What do? We group like terms and then we multiply. So we are going to have 3 times 4 times 10 to the power negative 4 times 10 to the power 6. 4 would give us 12. Then 10 raised to the power, we are supposed to add the power since they are multiplying. That's a law of indices. So negative 4 plus 6 would give us 2. So that would be our answer. Alright. Let's try another definition. Another form of division. Okay. So with this we are going to have 6 divided by 4 times 10 raised to the power negative 3 divided by 10 raised to the power. Every whole number has a power of 1, so we go by it that way. Now 6 divided by 4 would give us 6 divided by 4 would give us 1.5. And then when we are multiplying 10 raised to the power negative 3 divided by 10 raised to the power negative 1, we are supposed to subtract the 1 from negative 3, and that would give us 10 raised to the power negative 4. Okay, so that is how it goes. Now what if the division is given in fraction form? It is relatively easier to solve this. Now what we do is, if we look at the numbers 8.1 times 10 raised to the power 7, what we have to do is we have to change this to a whole number, so that if you look at it carefully, when we change 8.1 to 81, we can easily divide by 9. So this would be 81 times 10 raised to the power 1. We already had times 10 raised to the power 7. All over 9 times 10 raised to the power 5. Now 9 into itself is 1. 9 into each one would be 9 times. So this is going to give us 9 times 10 raised to the power 1 times 10 raised to the power 7. Remember, we add the powers, so that will give us 10 raised to the power 8 all over 1 times 10 raised to the power 5. And since they are divided, what we have here is subtracted from this, and our final answer would be 9 times 10 raised to the power 3. No need to write any form of denominator. Okay, so let's solve our next question. Now, since these numbers are all less than 1, we'll have to change them to standard whole numbers, so that it will be easier for us to cancel out. So going on, we are going to have 48 times 10 raised to the power negative. How many decimal places have we cleared? 4. 1, 2, 3, 4. So that is going to give us 10 raised to the power 4 times 81 times 10. We've cleared 2 decimal places, so raised to the power negative 2 all over 27 times 10 raised to the power. How many decimal places have we cleared? We've cleared 4 decimal places, so times 10 raised to the power negative 4 times 4 times 10 raised to the power negative 3, because we cleared 3 decimal places. Now let's cancel what we can cancel out. 10 raised to the power negative 4 will cancel 10 raised to the power negative 4, and then 27 into itself once, 27 into 81 would be 3 times. Now 4 into itself 1, 4 into 48 will be 12 times. So this is what we are left. 12 times 1 times 3 times 10 raised to the power negative 2 all over 1 times 1 times 1 times 10 raised to the power negative 3. And that is going to give us 12 times 1 times 3 would be 36 times 10 raised to the power negative 2 all over 1 times 1 times 1 times 1 times 10 raised to the power negative 3 will be 10 raised to the power negative 3. So what are we going to do? What we are going to do is we are to subtract this from this, so that would be negative 3, and that is going to give us 36 times 10. Negative 3 will become positive 3, so that would give us 1. But we are still not in standard form, so we have to write it as standard form. That will give us 3.6 times 10 raised to the power 2, because we have introduced 1 decimal place. So that is how it is solved. Now we also have 0.009 times 0.0012. All of these numbers are not in standard form, so it will be easier for us to express them in standard form and then easily multiply them. So we are going to have 9 times 10 raised to the power negative 4, because we have displaced 4 decimal places. Sorry, I think it's supposed to be 3 decimal places. Forgive my counting. Then times 1.2 times 10 also raised to the power negative 2. So to express this in standard form, 9 times 1.2 would give us that is 10.8 times, we are adding the powers of the tens, so that will give us 10 raised to the power negative 5. Now we will have to reduce this to give us 1.08. We have introduced 1 decimal place, so this has to go down by 1, so times 10 raised to the power negative 4. That is how it goes. Okay, so let's go on. So in solving this, we do the same thing. We have to write them, do our best to write them in whole numbers so that we can cancel out. So this will give us 125 times 10 raised to the power negative. How many decimal places have we cleared? 1, 2, 3, 4. So raised to the power negative 4 times 576 times 10 raised to the power 1, 2, 3, 4, 5. So negative 5 all over 15 times 10 raised to the power negative 4. We are clearing 4 decimal places, times 32 times 10 raised to the power negative 2, because we are clearing 2 decimal places. Now 10 raised to the power 4 will cancel 10 raised to the power 4, and then 15 will cancel 1, 2. That is 5 into 15 would be 3. 5 into 125 would be 25. Now 32 into itself would be 1. 576 divided by 32 would be 18. So in all, we are to have 25 times 1 times 18 times 10 to the power negative 5 all over 3 times 1 times 1 again times 10 to the power negative 2. 3 once again will go into itself, 1 into 18, 6 times 3 6 is 18. So we are going to have 25 times 6, or 25 times 1 times 6, and that will give us 150 times 10 raised to the power negative 5 all over 10 raised to the power negative 2. Of course, all of these are 1, so they don't really add value to what we are doing. So next, we are supposed to cancel this and then subtract. So we are going to have minus minus 2. Don't confuse yourself and ignore the minus. Okay, so it is supposed to be minus 5 minus minus 2, and these 2 minus becomes plus. So we will be having 150 times, this is going to give us 10. Since it is negative 5 plus 2, we are going to have negative 3. We also have to write this in decimal point, so a standard form, so that will give us 1.5 0 times 10. We are introducing 2 more decimal places, so this will have to reduce by 2, so it will be times 10 raised to the power negative 1, and that is how it goes. Now do your best and solve these questions and show the answer. Show the answer in the comment section. Okay, I'll be solving them, so you can pause the video here, try your hands on them, and then compare the answers. Okay, don't forget to try these questions too. Try these questions before comparing the answers. So we can view the answers now. This is the first screenshot. You can pause and view the answers, compare them. Then this is the second screenshot. Don't forget to comment any problem you had. Now we are to write this standard form in ordinary numbers. Again, pause the video and try this on your own. When you are done, you can compare the answers. Write them in ordinary numbers. Second screenshot. You can pause the video, come back, and then correct it. Compare the answers and check if they are the same. So this is the first screenshot. Compare your answers. You can pause the video and compare your answers. When you are done, you play. Second screenshot. Okay, let's move on. Okay, now we are looking at properties of operation. So we'll be looking about 3-4 types of properties. Now first, we should know that there are three major types of properties of operations. The operations we are talking about are addition, multiplication, subtraction, and division. So we'll look at commutative property, associative property, distributive property, closure property. Then we'll also look at a fifth property known as identity property. So first, when we say commutative property, what do we mean by commutative property? All operations are said to be commutative if A operating on B is equal to B operating on A. Okay, and this only works for addition and multiplication. If we should look at this, 1 plus 2 is equal to 2 plus 1. We are going to have 3, which is also equal to 3. In the same instance, 1 times 2 is equal to 2 times 1. We are going to have 2 equals 2. But when we try that for subtraction, it is not the same. 1 minus 2 is not equal to 2 minus 1, because we are going to have negative 1 here, which is not equal to 1, as we are going to have here. In the same instance, 2 divided by 1 is not equal to 1 divided by 2. So as this will give us 2, on the other hand, we are going to have 0.5 or half. Okay, so commutative property only works for addition and multiplication. And this tells us that if adding 15 to 25 is a problem, you can flip them to make it 25 plus 15. Okay, your answer would surely be 40, no matter how you arrange them. In the same way, if 2 times 8 is a problem for you, then you can solve it as 8 times 2. You will get 16 in both cases. So that is the essence of properties of operation. And commutative property means that no matter which number you place first, you always get your answers correct. We are going to look at associative property. It is similar to commutative property, but here we are dealing with multiple numbers. Okay, it still also works for only addition and multiplication. So in this case, we are saying that if you operate on 3 numbers or more, the sequence of operation doesn't really matter. So whether you solve A operating on B first, then you later on solve the answer operating on C, it is still correct as solving B operating on C first, then later on operating A on the answer you are going to have. Let's try that. 1 plus 2 plus 3 should be equal to 1 plus 2 plus 3. 1 plus 2 is 3 plus 3 would give us 6. We are going to have the same 6 here. When we try multiplication, 1 times 2 times 3, it is still equal to 1 times 2 times 3. Here it doesn't matter if we solve this first or if we solve this first. Let's go back and correct, and let's do it by that operation, and then let's see. 1 plus 2 will give us 3, then plus 3 would give us 6. It's the same as what we did earlier on, just want to make it clear. Then 1 plus 2 plus 3 is 5. We are still going to have 6. So that is associative property for you. Now when you have 2 times 3 times 4, it should be equal to 2 times 3 times 4. It doesn't matter if you solve 3 times 4 first or 2 times 3 first. 2 3 is 6. 6 times 4 is 24. On the other hand, 3 4 is 12. 12 times 4 is also 24. So it works out just like that. It doesn't work for subtraction and then division. You can try this on your own and then check if the answers will be correct. 2 4 minus 3 minus 2. You realize they are not equal to. So this will be your answers. You realize that both sides are not equal. Now let's try distributive property. Now with distributive property, we say that addition and subtraction are distributive over multiplication and division. So let's keep that in mind. So what we are saying is that if we have A plus B in bracket and they are all multiplying C, it could be expanded into A times C bracket close plus B times C. It could be done it could be changed from this to this or from this to that. So let's assume we have 2 plus 3 all multiplying 4. The multiplication will not always be written. It could be written as 2 times 4 plus 3 times 4. Let's solve the left hand first. This would give us 5 times 4, and that will be 20. And we are going to have 12. We are going to have 8 plus 12 here, and that also gives us 20. So that is what we mean by distributive property. It also works for division. So anytime you have two numbers adding or subtracting in a bracket, and they tend to multiply a number outside, it could be 3, 4, 5 numbers in the bracket, and the answer is supposed to multiply a number outside like we have here. You can decide to expand first, or you can add and then you solve. It doesn't change anything. With the closure property, it depends on the subset you are given. So sets could be given, let's say 1, 2, 3, 4, 5, 6, and you'll be asked to operate on them. If you operate on them and all the answers you obtain can be found in this set, then we will say that your operation is closed on this set. So most of the time, the operations we do are all said to be closed on what? The set of what? Real numbers. Okay, because most of the time you are either going to have a rational number or an irrational number, and they are all subsets of real numbers. So that is what we mean by closure property. We are comparing your answers to the answer in a set. If your answer can be found in a set, then we can say that the operation is closed on the set. For instance, with this set, if I give you 4 plus 2 plus 1, your answer would be 5. Since we have 5 here, the operation plus is closed on the set. It's as simple as that. Now let's look at identity property. When you say identity property, we are referring to the various numbers that do not change the number being operated on. Let me explain. If I should have 20 times 1, my answer would still be 1. It will still be 20. 100 times 1 will still give us 100. 30 times 1 will still give us 30. Immediately 1 changes, the value also changes. So because the identity of the numbers being operated on haven't changed, we say that 1 is the identity for multiplication. 1 is also the identity for division. So any number divided by 1 will give us that same number. So that is to say that the identity property for division and multiplication is 1. For addition and subtraction, it is 0. The identity property for addition and subtraction is 0. 3 plus 0 is still 0. 16 plus 0 is still 0. 5 minus 0 is still 5. 15 minus 0 is still 15. So for multiplication and division, the identity property is 1. And then for addition and then subtraction, the identity property is 0. So that is that. Now we have what is known as binary operation. Now some operations are not really defined because we already know them. So when we are given addition, subtraction, multiplication, and division, we already know them. But sometimes the operation of one number on another has a multiple of these. Okay, and we refer to that as what? Binary operation. In such a case where the operation is unknown, it will be defined to the individual like we have in the example here. If we look at what we have here, we are being told that m star n is expressed as mn, m plus n plus mn. So in other words, if I have 1 star 2, this is supposed to be worked as 1 plus 2 plus 1 times 2. Okay, so this is how we are supposed to work on that. And when we've been asked to use that to evaluate 3 star 4 and then 4 star 3. So let's work them out and then let's see. This is going to give us 3 plus 4 plus 3 times 4. Working this out would give us 3 plus 7 is 4. 3 times 3 plus 4. 3 plus 4 is 7. Plus 3 times 4 would give us 12. So 7 times 12 would be 19. When we are to work 4 star 3 out, we are going to have 4 plus 3 plus 4 times 3. Again, 4 plus 3 is 7. 4 times 3 is 12. So 7 plus 12 will give us 19 again. So we could tell that there is associative property here. Now B is asking, compare your answers in I and II. We can see they are the same. What property is that? So we could say that this is associative property. So we could say that it is not associative, it is rather commutative. Okay, it is rather commutative property. And see, we've been asked to show that these two operations are the same. So to translate them, this is what we are going to have. So working it out, this is what we are going to have. And we can tell that this is associative property. So we are looking at our second question on binary operation. And the question reads, the operation star is defined by A star B equals half A minus B. Form a table for the operation on the set 4, 6, 8. II is the operation commutative, and why? And if A equals 4, B equals 6, and C equals 8, evaluate A star B plus C, and A star II, AB star B plus A star C. Let's see how this goes. So first we are going to draw a table for the set 4, 6, and then 8. So we have star here, 4, 6, 8, 4, 6, 8. Okay, so first we have 4 star 4, 4 star 6, 4 star 8, and that is supposed to give us the definition for the operation is half A minus B. So this is going to give us half of 4 minus 4, and that will give us 0. Because 4 minus 4 is 0, and we go ahead, we are going to have 0. Then half 4 minus 6, that will give us half of negative 2, and that equals negative 1. And then we have half 4 minus 8, that will be equal to half minus 4, and that will be equal to negative 2. Okay, so let's erase this part and then let's go on with the rest. Now we are picking 6, so 6 star 4, 6 star 6, and then 6 star 8. This would give us half 6 minus 4, which will give us half of 2, which equals 1, which will give us half 6 minus 6, which will be equal to 0, and then half 6 minus 8, which will be equal to half of negative 2, and that will be equal to negative 1. Now let's go on and deal with our last line. That will give us 8 star 4, 8 star 6, 8 star 8. Now this would give us half 8 minus 4, and that will give us half of 4, which is 2. Half 8 minus 6, that will give us half of 2, which will give us 1. Half 8 minus 8, which is equal to half of 0. Basically we'll be having 0. So our answers are 2, 1, 0. So we are done with our table. The next question says that, is the operation commutative and why? We are supposed to check if the operation is commutative. Now for the operation to be commutative, for start to be commutative, A star B should be equal to B star A. So if we look at it, 4 star 8 gave us negative 2, 8 star 4 didn't give us negative 2. That is 4. So from the table, four star 8 is not equal to 8 star 4. Therefore, the operation star is not commutative. Now see, we are supposed to see I. We are being told A is 4, B is 6, and then C is 8. So we are supposed to find I. A star B plus C. So that would give us A. A is 4. That will be 4 star 6 plus 8. And that would give us 6 plus 8 would be 14. And then 14 star 4 would give us half 4 minus 14. That will give us half of negative 10. And that would give us negative 5. Now I says we should find the expression. This is I right here. A star B plus A star A. So you are supposed to find A star B plus A star C. Okay, A star B plus A star C, each in their own set. So A is supposed to be 4, B is supposed to be 6, plus A is supposed to be 4, C is supposed to be 8. So this would give us half of 4 minus 6 plus half of 4 minus 8. This would give us 2, that is negative 2, plus half of negative 4. Half of negative 2 is 1, half of negative 4 is negative 2. So summing them up, we are going to have negative 3. Okay, so basically that is that. I think question C was trying to test for associative property, but for distributive property, but as we can see, it is not distributive. Yeah, it is not distributive. Now this is question 3. The operation star is defined on the set of real numbers by m star n equals m minus n all over n, where n is not equal to 0. So based on that, we are supposed to evaluate. So let's go ahead and then let's solve this. So 3 star 5 star 2 would be equal to 3 star. We solve what's in the bracket first. That will give us 5 minus 2 all over 2. And that will give us 3 star 5 minus 2 is 3, so 1.5. So 3 over 2 gives us 1.5. And when we express this, we are going to have 3 minus 1.5 all over 1.5. So 3 minus 1.5 is going to give us 1.5 all over 1.5, which is equal to 1. Now let's try solving for II. We have to find the truth set of A star k equals 12 star 3. So all we have to do is express that. So BI, we have 8 star k, 8 star k is supposed to be expressed as 8 minus k all over k, and that will be equal to 12 minus 3 all over 3. So this implies we are going to have 8 minus k all over k equals 9 over 3. Okay, 3 into itself 1, 3 into 9 would be 3. Okay, so this is what we'll be having. So we're going to have 8 minus k all over k equals 9. Then we can cross multiply. Okay, 9 is over 1. So 1 multiplies 8 minus k. We are still going to have 8 minus k. And then k times 9 is going to give us 9k. So we move k to the other side. So this is going to give us 8 equals 9k plus k, since it was negative. Then we have 8 equals 10k, dividing both sides by 10. So 10 dividing 10k would give us k. I wish I would get 10k views here. Help me share the videos. Then 2 into 10 would be 5. Then 2 into 8 would be 4. So this implies that k would be equal to 4 over 5 or 0.8. Now let's try BII. We have k star 8 equals 12 star 3. So k star 8 equals 12 star 3. So that is going to give us k minus 8 all over 8 equals 12 minus 3 all over 3. So going on, we are going to have, let me go horizontally, k minus 8 all over 8 equals 9 on 3. Cancelling out, we are going to have 3 on 1. So k minus 8 over 8 equals 3 on 1. We are going to cross multiply, and that would give us k minus 8 equals 3 times 8, and that implies k minus 8 equals 24. We transpose 8 to the other side. K will be equal to 24 plus 8. K equals 32. Yeah. So that is how we go by solving such a question. Now we were supposed to state the truth set. So to state the truth set for I, we go that x is such that x equals 4 over 5 or 0.8. You close your curly brackets. Here we have k is such that k equals 32. You close your curly brackets. You're good to go. So that sums up our video for numbers and numeration. Thank you for being with me through this journey, and enjoy the rest of your day.